So today, Dr. Bo Wan will present seismological evidence for the earliest global subduction network at 2 billion years ago.
So thanks everybody. So this is a new published work. It's very honor for me to share with you, and I will not repeat the title. So the color different is our co-authors, and this is a collaboration work between different subjects. And I'm a geologist in black, and this blue are three seismologists from our institute and from Macquarie University, and we and Ross are expert on the paleomagnetism. So before, I would like to briefly introduce what is plate tectonics. So the plate tectonics basically describes the surface kinematics. So all these plates, they have different boundaries. So they have the divergent boundaries. So the plates move horizontally from different directions. And also they have the convergent boundaries. So you have material recycling from surface to the deep mantle. And also we can see the slabs use the tomography from the surface to the deep mantle and in the mantle transition zone. But one of the most important characteristics of the plate tectonics is the global network, because all these plates are not moved independently, they move mutually together and they connect with each other. So the global network is very important to describe the plate tectonics. But when did plate tectonics start is one of the biggest arguments in the earth science community. So you can see this is a chronological figure, the diagrams. So we can see the earliest evidence is 4.2 billion years ago by Hoskin, the zircons, and the youngest is even younger than the 1.1 new Proterozoic. And the biggest argument is all previous studies mostly focus on one evidence, like the earliest evidence for recycling or the horizontal motions or the geophysical images, like this is the sharing use diamonds. They show the material recycling is very old time, and this is from Greenland from Maruyama's group, and you can see the foldings, like they folded together. They folded a very large scale horizontal motions, and this is Chen's paper about the seismic evidence, one of the earliest in the slab cratons. And the global network starts very young, proposed by Boston, and it may be younger than 1 billion years. So there is a huge gap between this earliest evidence and the network. One potential area in Earth history is the Paleoproterozoic in Ordos. This is the age between 2 billion years and 1.8 billion years. During this time, there are many organic belts. This is the reviews by Professor Zhao and Professor Condi. There are from 20 to 34 collisional belts. Although we have so many collisional belts, but we cannot, we just cannot automatically prove they are connected each other. And so we still need to prove they are connected with each other. So before we started, we have to show that the North China have connected with the Siberia. In 2015, we do a large scale mapping in the northern margin of North China craton, and we found that these different colors represent different rocks. This is a gneiss, and this is a limestone. This is a olivine and garnet bearing websterite. It's a high pressure rocks, and this is a gabbro in the gneiss, and the gabbro intruding into the garnet websterite. And this is here is the basalt and mudstone. Here is the mudstone. And all these rocks are thrusted with each other. So this map tells us these rocks are from different places. They mutually come together in one in cratonal wedges. And we found these rocks experience very high pressure metamorphisms. And this rock is very similar to one rock in southwestern margin of the Siberia. They basically have the same PT path. You see this red is our rock and the green is the Siberia rocks. So we use these two rocks to connect the North China and the Siberia. And this is our finding. And also we have a confluent belt in the north margin of the North China Craton. So we're thinking, because we already have the ophiolite melange here, we have the high pressure rocks here, and we are thinking if the North China, the deep crust also record these subduction structures. So this is our 2015. Many different groups also found many evidence along the northern margin of North China Craton, and this is the one melange in the Bayun area in North China, in the northern margin of North China Craton, and these two stars are the very cold subduction. It's also in the Paleoproterozoic age. It's in this area. And the North China Craton is a very stable, especially the Ordos block here. So you can see this is the very previous seismic profile in the interior of the Ordos block here, and you can see that all the surface. This is Chinese, sorry, and I put the English name here. It's a craters, Jurassic, Triassic, Permian, and this is the Changcheng group. It's a Mesoproterozoic strata, and all these strata are basically undeformed. And this is the Paleoproterozoic basement. You see, this is highly deformed here. So the deformation of this is basically in the Paleoproterozoic. And the Changcheng group, after that, after Mesoproterozoic, is basically stable and non-deformed. And this is the surface rocks. You can see this is the Changcheng group. This is the Changcheng group, an unconformably deposit on the Paleoproterozoic basement. And here I put a right line here. It's just mark the foliation of the basement. You can see. So I say the Ordos block is very stable based on this seismic and reflection and geological evidence. And also this black line is the draw hole. They show that this is the different ages of the strata and the basement. And this is from seismic evidence, you see. This is the receiver function result. You can see the Ordos block. This profile is this line. You can see the Ordos block is very typical craton structure. They have very thick lithosphere root. This is a very classic one. And this surface geology also tell us the Ordos block are very, very stable. This black are the faults, and this red is the Phanerozoic magmatum. So we did not see any magmatums and metamorphisms, Paleozoic age in the Ordos block. So in this background, so we deployed a very high density profile, seismic profile across North China Craton, north margin of North China Craton. Here is inside of the Ordos block and across the continental belt and across the boundary of the North China Craton and the Central Asia Organic Belt. And this is how the profile looks like, very high density. So each station, two stations are 500 meters away each other. This is the result. We use the receiver functions to map the deep structures. And because this is the positions of the earthquakes, you can see we have 3 earthquakes from the southwest in the Indian Ocean, and many about 15 earthquakes from the Pacific Oceans. And we see that the earthquakes from the different directions record the different structures. From this red represent this red. So the earthquake from the southwest see the deep structures, but from the southeast we didn't see these deeping structures. It is because, so we also forward modeling what happening. So if we forward modeling this, so we can see that if the deeping structure is deeping to the northwest at 300 deeping to the northwest to the 300, and the deeping angle is 30. So the modeling show that we can see the earthquake, the deeping structure in this area, and we cannot see the deeping structure from this area. You see, because all the Pacific regions, the earthquake in Pacific regions are located in this area, so we didn't see the deeping structure here. And also we don't have earthquake in the, how to say it, Arctic Ocean. So we only have the earthquake from this area. So we can see the deeping structure here like this. So we successfully modeling this. So the earthquake from the southwest record the deeping structure. So we have the, like I previously said, we have the ophiolite. It's about 1.9 billion years old, and we have the deeping structures like this. Here is about 1.82 billion years, and also previous studies from this area show that they have some granites. They have very strong signals of crust recycling. You can see that material recycling. And this is a half-human isotope. So you can see this is the depleted mantle. So you have a mantle and a crust mixture. So this is kind of the crust recycling. So the seismic data is consistent with the geological predictions. So we also use the CCP method to put all the signals together. You can see clearly that the deeping borehole here beneath the Ordos, stable Ordos block, and you see this almost flat at the northern of the Ordos block into the Central Asia oceanic belt. And these structures are 1.8 billion years ago. It is very similar to the modern day Himalaya structures. This is the Nablik structure. A Nablik image use the receiver function in Himalaya. You can see this is 50 kilometers. This is 55 kilometers. You can see the deeping structure, the scale are very similar. Also, the surface geology is also very similar. This is the big thrust here. So we have the high grade rocks. This is Contlet belt here. We have the sutures here, and this is the Himalaya. They have this is maybe MBT or MCT, and here is the high Himalaya metamorphic rocks here, and this is yellow Zambud sutures here. So the North China is geophysical and geological, identical to modern Himalaya. And this kind of structure are recorded in many different places. And this is the very early times paper bubble group Nature in Baltica. You see this structure. And this is in Laurentia. And this is in West Australia by Johnson, published in Australia Journal Earth Sciences. And they also have the geological evidence. This is the one of the most famous ophiolite in the older time, Juma, and this is the blueschist in the Laurentia, and this is the high pressure rock ophiolite in the Siberia. And the previous studies speculate that Nuna is one of the oldest supercontinental. And they proposed the Laurentia and the Baltica are very stable connection. And after that, many different groups also proposed the Baltica-Laurentia-Siberia. are the core of Nuna. And this is the Evans paper, and this is George paper. Also, different papers all agree that the Baltica-Laurentia-Siberia are very stable connections. And our work just puts the North China into the core of the Nuna based on the geological and geophysical evidence. So we increase the core of the Nuna, and this is the new updated version of the reconstruction by Ross and Uwe. And one lesson from the plate tectonics that the subduction of the slab driving the plate motion. This is the velocity of the plate, and this is the change, the length of the change. They have a very linear relationship. Our previous work in the Titan belt also suggests that the plate driven can from the Cenozoic to the whole Phanerozoic, because the Titan belt is basically from the early Paleozoic to Mesozoic. So our work suggests that all the big Nuna core can sutured by only 2 or 3 big sutures, because the subduction drive the plate and direct the plate motions. So probably the subduction driving plate can form the Cenozoic to Paleozoic to the Paleoproterozoic. So these figures just show that the plate motions drive all the plates together. And this is a very new modeling based on my colleagues prepared, and modeling the oceanic crust thickness at 30 kilometers. Because we said the plate assembly needs the plate drive a long time. And if the oceanic, because in the Archean time, the oceanic crust may be over 30 kilometers, and this modeling showed that you can see some kind of the subduction, but it's detached very soon, almost detached after 9 or 8 million years. And the horizontal motion are also very small scales, maybe 200 or 300 kilometers. So it tells us that in the Archean time, the plate just cannot move 1,000 kilometers. So our work just suggests the subduction network maybe started at 2 billion years ago. And because of the subduction network, they assembled the first Nuna supercontinental. So our work just fill the gap between the earliest single evidence from one place and the global network here. Thank you. And this is how Ordos looks like.